Gravitational collapse occurs when an object's internal pressure is insufficient to resist the object's own gravity. For stars, this usually occurs either because a star has too little fuel left to maintain its temperature through stellar nucleosynthesis, or because a star that would have been stable receives extra matter in a way that does not raise its core temperature. In either case, the star's temperature is no longer high enough to prevent it from collapsing under its own weight. The collapse may be stopped by the degeneracy pressure of the star's constituents, allowing the condensation of matter into an exotic denser state. The result is one of the various types of compact star. Which type forms depends on the mass of the remnant of the original star left if the outer layers have been blown away. For example, in a Type II supernova, the mass of the remnant, the collapsed object that survives the explosion, can be substantially less than that of the original star. Remnants exceeding 5 m are produced by stars that were over 20 m before the collapse. If the mass of the remnant exceeds about 3 to 4 m, the Tolman-Oppenheimer-Volkoff limit, either because the original star was very heavy or because the remnant collected additional mass through accretion of matter. Even the degeneracy pressure of neutrons is insufficient to stop the collapse. No known mechanism, except possibly quark degeneracy pressure, is powerful enough to stop the implosion, and the object will inevitably collapse to form a black hole. Quote, "The gravitational collapse of heavy stars is assumed to be responsible for the formation of stellar mass black holes. Star formation in the early universe may have resulted in very massive stars, which upon their collapse would have produced black holes of up to 103 m. These black holes could be the seeds of the supermassive black holes found in the centers of most galaxies. It has further been suggested that massive black holes with typical masses of ~105 m could have formed from the direct collapse of gas clouds in the young universe. These massive objects have been proposed as the seeds that eventually formed the earliest quasars, observed already at redshift z operator 7 _z sim 7. Some candidates for such objects have been found in observations of the young universe. While most of the energy released during gravitational collapse is emitted very quickly, an outside observer does not actually see the end of this process. Even though the collapse takes a finite amount of time from the reference frame of infalling matter, a distant observer would see the infalling material slow and halt just above the event horizon. Due to gravitational time dilation, light from the collapsing material takes longer and longer to reach the observer. With the light emitted just before the event horizon forms delayed an infinite amount of time. Thus the external observer never sees the formation of the event horizon. Instead, the collapsing material seems to become dimmer and increasingly red-shifted, eventually fading away.